Greetings everybody, and welcome to our example 7 in our series on cross products. So what we're asked to do in this case is to use determinant notation to find the cross product of our two vectors u and v. So before we actually use determinant notation for this, we can just compute these vectors kind of algebraically, and then we'll look at the determinant notation. From that point, it really is totally up to you how you like to compute them. Find the method that you like the best and use that. And so if we're doing this algebraically, what would it look like? Well, we're doing u cross v, and so that will be a minus 5i plus j minus 7/2 k crossed with our vector minus 5i minus 4.5k. Now, in computing these algebraically, remember that we have our cycle notation, where we have our I cross j is going to give us k. Then, permuting these things cyclically, we just shift everybody over one place. So we have j cross k, giving us I, and then finally k cross I, giving us the value of j. Then we're using the fact that for any of the reverse operations that we have anti-commutativity, and for that one, if we reverse the cross product, so v cross u is going to be the negative of our u cross v. And likewise, if we have a vector crossed with itself, remember we have this property that v cross v is going to give us the zero vector. So with these things in mind, we can use the distributive property to compute our cross product algebraically. And so remember, what happens is that our vector in one set of parentheses is really just going to distribute and cross with all of the other vectors. Likewise, for our second vector, it will do the same thing, and it will distribute and cross with all three of the vectors from the first set of parentheses. And so what we have then is a minus 5i times a minus 5, or a minus 5i cross a minus 5i, but then I cross I is going to give us 0 automatically. So anytime we have a vector crossed with itself, we can just ignore those because we'll have the 0 values. And so for those, they will automatically be 0. So what we have then is our minus 5i, and we're crossing that with j, so we have a minus 5 with the j cross I, because j is on the left. Then we have a minus 7/2 times minus 5, so that will give us a plus 35/2 of k cross I. And then distributing our k, we have a minus 4.5 times a minus 5 to give a positive 22.5, and we have I cross k. Then we have our minus 4.5 times a positive 1, so we have a minus 4.5 j cross k. And then finally, we will have the k cross k, but that one will also give us a 0. So now coming in and using our cyclic permuted properties, what we have is with a j cross I, that becomes a minus k, a 35/2. Our k cross I becomes a j. We have a 22.5. And then our I cross k is also going to give us a minus j. And then our j cross k is going to give us an I. So now kind of combining any like terms that we have and kind of putting things together, we have a minus 4.5 times in the I direction. Then in the j, we have a 35/2 and then minus 22.5. to give us a minus 5j, and then finally the minus 5 times the minus k gives us a plus 5k. And so we can see that our answer is actually going to be part B. And so now to see what this would look like in determinant notation, we compute this a second way. So to compute this with determinant notation, we list our unit vectors across the top in the first row of a matrix. So we compute that as I, j in the second column, and k in the third column. Then we put our vector u on the second row because we're computing u cross v. So that will become a -5. And then we have a 1, and we have a -7/2. And then finally, for our v, we have a value of -5 in the I direction, 0 in the j direction, and a -4.5 in the k direction. And so we want to compute this 3 by 3 determinant. Well, how we do that, we take the first entry of the first row, and so that will be our vector I, and then the determinant that we use to compute the I component will be the determinant where we get rid of, or we ignore, the first row, and we ignore the first column. And so what that will give us is our determinant 1, -7/2, 0, and -4.5. Then for our next entry in our first row, we're using a j, but because this is a 3 by 3 determinant, we change the sign, and so that one will be a -j times our 2 by 2 determinant, where we again get rid of our first row, and now we get rid of our second column. And so that will give us a 2 by 2 determinant of -5, -7/2, -5, and -4.5. And then finally, for our third component, we use our third entry along the first row, which that is k, and we ignore now the first row, and we ignore the third column, and so that will give us a 2 by 2 determinant of, that will give us a 2 by 2 determinant of -5, 1, -5, and 0. So now to recall that how we compute a 2 by 2 determinant, that if we've got a value a, b, c, and d, that we compute the determinant by taking the difference of the diagonals. So we've got a times d minus b times c. And so what that gives us in this case will be I times our value 1 times a -4.5 minus 0 times a -7/2. Then our minus j times our main diagonal, so a -5 times a -4.5 minus a -5 times a -7/2. And then finally, for our third component, we have k times our determinant, -5 times 0 minus a -5 times 1. And so when we simplify each one of these expressions, what we end up with is a -4.5 in the I direction, and then a -5 in the j direction, and a +5 in the k direction. So that's using determinant notation and using the algebraic expansion. And so I hope you've enjoyed this. I hope you see both methods. Choose the one you like the best and go with it. And I will see you guys in the next video. Take care.